This is a step 2 question from 1992. It's question 10. It's also question 1 from the step 2 complex numbers support book. A couple of things to say before we do this question, particularly for the first couple of bits. All of this stuff, all the theory that you need for these bits here is in the FP2 Edexcel textbook or Pearson Edexcel textbook. So if you do that at school, and maybe your teachers have some spare copies of that book lying around because you haven't studied it actively, that would be really helpful to help you out, do some more practice of this kind of idea. Second thing is that Eddie Wu has an incredible series of videos on this exact topic. I think it's called something like Arcs in the Complex Plane, something like that. He made it a couple of years ago, so I'm sure you can all find it. But anyway, let's get into it. So if you do want further reading, those two resources would be fantastic for you. So we have the argument of this over that equals alpha. Now, of course, arguments that are dividing are just subtracting. So argument of this minus argument of that equals alpha. And that's the first thing we'll say. Let's actually dial down what argument of this minus that means. If you have the argument of z minus w, where z is some complex number and w is some complex number, this means the angle from the point w to the point z. So, for example, if we had these two complex numbers, z here and w here, the argument of z minus w would be, well, parallel to the real axis across here, and then z from w to z would be this angle here. And if you want some justification for why that is, think of an easier case, right? That's always the way to go. So let's just think about z minus 1, which is actually what we've got here. If we pick the point 1, obviously that's there. And z can be any point on this line, as we know from like year 12 further math stuff. Z is any point on this line, so therefore the argument of z minus 1 is the argument or the angle from the point 1 to the z here. So that's the justification for that. So okay, that's what we've got here. So let's call that theta and that mu. And let's do both these things. So one of them is measured from 1. You can think of z as just z minus 0. So one of them is going from 1, and one of them is going from 0. Like this. And where's theta minus mu? Like, where is that? Where is that in this picture? Well, okay, we're in radians for this. So this is therefore pi minus theta, because pi on a straight line. And there's also pi in a triangle. So this angle here is pi minus mu minus brackets pi minus theta, which I believe two negatives cancel and you just get theta minus mu. So this is the angle alpha that's being discussed. So this question is talking about this specific angle alpha. We're looking for values of z. So this would be z. We're looking for values of z such that the angle measured to 1 take away the angle measured to 0 is alpha, which in this case here it is just because it is. So we're looking for a sketch of all the points z could be to make this situation happen. So for example, if I go over here and call this angle all the way here mu, and this angle all the way here theta, and do mu minus theta, which is always here, maybe that also gives me alpha. Maybe. It looks like it kind of does. And maybe this picture jogs some memories, because the theory, in order to get the same alpha every single time for any value of z, is hopefully back from GCSE stuff. If you draw pictures like this and you get 30 degrees and you get 30 degrees and you get 30 degrees, apologies for the messing around between degrees and radians, but whatever. The theory from GCSE says this is a circle. It's this theorem that you'll hopefully recognize that I stole off Google. You make circles when you have equal angles subtended from the same chord, I think or same arc. I'm not sure. Same arc. I think that's the name of it. And yeah, so essentially when we go back to here, what we're going to do if we're looking for a consistent alpha every time is we're just going to be looking for a bunch of z's that put us in a circle. Now the thing is, there's a couple of situations you could be in, because if that angle is 30, then sure, you make a circle that looks like that. But if the angle is 90 that you're searching for every time, your circle is perfectly split in half with the diameter going through the 2 points that you're starting at. Right, that's the alternate circle theorem, which people present as a different rule, even though it's the same rule. It's just a rule with a specific 90 rather than any angle x. However, one more case that you don't explicitly discuss at GCSE as much is what if you're searching for a really big angle, like 120? If you're doing that, then it turns out that you make the minor arc of a circle. Specifically, you make sort of this top edge of it rather than the larger edge we saw when we did 30 degrees. So if theta is less than 90, it's going to be a major arc. The thing you're going to be doing is the major of the two arcs, it's the larger of the two. If it's 90, it's equal arcs, and if it's 120, it's the minor arc. Sorry, if it's greater than 90, it's the minor arc, not just 120, of course. So in our case, alpha is between 0 and pi over 2, which is, of course, acute. So therefore, this is going to be the major arc of a circle. So all of our values of z's that work is going to create the large arc up here. Now be careful, we're not going to have this thing down here. We're going to need to scrub that out from the picture. And the reason we're going to scrub this out from the picture is because if you actually draw it in, what you'll see is that this angle down here, because of angles in a quadrilateral adding up to, in this case, 2 pi, of course. No, sorry, yeah, 2 pi, of course. That's not even the rule, is it? Angles in a cyclic quadrilateral, of course, add up to 2 pi because it's a quadrilateral, but the opposite angles in a cyclic quadrilateral add up to pi. So this is not alpha down here. This is pi minus alpha, the angle being created between them. So therefore, we scrub that arc out from it, and it's just going to be the top side. Of course, we just saw that the angles in the minor arc are going to be the larger part. So unless alpha is specifically 90, or pi over 2, of course, then these two things are not going to be the same. So therefore, we're going to scrub that away from it. Now, this brings us on to the next part. And by the way, this is the entire picture, nice and complete. Now we're going to look at the next part. And this should look familiar, alpha minus pi. Well, that's basically what I just wrote down here, right? Underneath the x-axis, pi minus alpha. So alpha minus pi, well, alpha is less than pi. So therefore, this is a negative number. And that's just because arguments measure become negative when you measure the wrong way around. So it's exactly the picture that I just drew down here. And you can do lots of algebra if you want to prove to yourself that this is definitely pi minus alpha, but it is just because of the cyclic quadrilateral that we saw before. But of course, because alpha minus pi would give you a negative number, we're just going to write, in our maths, it would come out as pi minus alpha because that's just a positive number. But arguments work with negatives, that's fine. So therefore, this is definitely the arc down here. Eddie Wu's video goes into more detail about kind of which way round the arc you're traveling, if you want to have, like in terms of direction. So just go watch that if you're more interested in that kind of idea as well. The other thing I'll say to justify this is that, of course, if alpha minus pi is less than 0, which it is, then that means theta must be less than mu. So, okay, well, theta is the angle coming up this way somewhere. I don't know why I've got these thetas and mu's here. They should be deleted probably, but yeah, whatever. But theta's coming out this way somewhere. Mu is bigger, so it's going off this way, which means they're never meeting the top side, right? They're only going to meet if you continue drawing them down the other way. And so that's the other justification we have for them being down here, I guess, as well. This is a weirdly easy question for them to throw in here. I'm not sure why they've done it. Firstly, when you have a mod of a fraction, you can just take the mod at the bottom and top separately. To justify that, of course, this whole side is positive because you're going to mod it after you do the fraction. So you may as well just do the mod at the top, do the mod at the bottom, and then you're doing two positives divided by each other. So that's the justification for why we can do that. I know mods aren't really that in the complex world, but let's just pretend they are. Anyway, we can do this, times it both sides by z modded, I guess. Cool. We can think of z minus 1 as the distance from z to 1, and this is the distance from z to 0, because of course this is z minus 0. So we're looking for the distance from z, we're looking for all the points that exist here, such that the distance to 1 is the same as the distance to 0. So we put down 1 and 0, and we think, well, here's an obvious point, and then here's another obvious point, making a nice little isosceles triangle, and then there's another nice one, and yeah, we've done this in year 12 complex numbers, so that's all fine. We just get this. I'm not sure why they put that question in there, if I'm completely honest. Just for ease, on this last part of the question, it's a really good question, we're going to call this A, this B, this C, and this D real quick. Okay, we've got 4 points Z1, Z2, Z3, Z4 on a circle in that order, so it looks maybe a bit like this. Now, if we call this A, B, C, and D, of course, if we take the argument of W, what we can do is, obviously, we can take the argument of both sides, but this is the argument of a bunch of things multiplying and dividing. So the things multiplying will add, and the things dividing will take away. So this becomes this, because these two things are on the top, and these two things are on the bottom. Those two things will take away, and those two things will add. Now we can replace those back with the things that they originally were. And now this is why we discussed right at the very start what argument of Z1 minus Z2 really means. This is the angle from Z1 to Z2. No, it's not. That is complete rubbish. This is the angle from Z2 going to Z1, measured parallel to the x-axis. So, of course, if you maybe draw this in the picture, from Z2 means go across from Z2, a bit like bearings, I guess. You're going to Z1. So that's that angle there. Let's just call it theta. And let's do the same for all of the others. So Z3 across from Z4, from Z4 to Z2, of course, Z3, of course. So across from Z4 to Z3 is all of this angle. So let's just call that maybe mu. And then the same for the other ones as well. Let's be super careful about all this. So that's delta. And then this one lastly will be gamma. Okay, now show by considering arg of W, so that's what I'm doing, that W is real. Now, what does that even mean? Now, if W is real, then in the imaginary axis plane thing, it exists on the real line. So that means either I'm looking for argument of W to be 0, because it's here somewhere, or argument of w to be pi, if it's over here somewhere, where the argument will be pi. That's what I'm looking for. So I'm looking for argument of omega. Did I say w earlier? We know it's the same thing. To be either 0 or pi, right? That's what I'm aiming for. So, okay, is there anything in this picture? I have that arg of w is obviously this plus this minus this minus this. Is there something in the picture here that tells me, why have I done a minus here? What is this? Why is that a minus plus delta? What am I doing? Oh, of course, because theta is measured down like this, so it's going to be a negative argument. So is delta, but delta is already taking away. So it becomes a positive, and mu, yeah, sorry, that took me embarrassingly long to figure out what I'd done there. So anyway, yeah, some of these arguments cancel and become negative, and then become positive again. So that's all cool. So no, anyway, we're trying to show that this is either 0 or pi for w to be, or omega to be real. So okay, let's look in this picture and see what we can do. See if we can cancel some things out somehow. Because there's lots of hope here, right? It's a cyclic quadrilateral, so we've got some rules. We've got lots of alternate angles going on, I can see already, so that's all fantastic. So let's have a look. Let's just call this angle x, maybe, and let's call this angle down here y, I guess. And now let's come up with some equations here. So, of course, x plus y is pi, because cyclic quadrilateral things, so that's all fine. We can also say that this angle up here maybe is gamma, which means we have gamma plus x plus theta is also pi. And then also, I guess the other thing we can say is that this one here is delta. Now, delta is actually, if that's delta, alternate says that all of this is delta, all of that. So therefore, looking at this straight line here, delta plus mu is, I think, pi. But also, it's not quite right, because delta plus mu overlaps this little section here, because mu is all of that, remember? And delta is all of that. So I'm going to have to take away y, which is why I put that y in there, take away y to sort of cancel those two bits out, and we get delta plus mu minus the double bit, which is precisely y, equals pi. If I think if I just sort of take away those results from each other, we end up with this. Take away all that in bracket, swaps that sign over. But x plus y is precisely pi, as we said before. So we end up with this, which ends up obviously with this. And if you look at this, the terms are written in the wrong order, but it is precisely the same thing, and we end up with argument of omega is pi, which is exactly what I was talking about earlier. If the argument of omega is pi, then that means it ends up exactly on the negative part of the real line, and so therefore omega is a real number that's, I think, negative, I guess. And that's the whole question. Thank you for watching, and I'll see you next time.